Hello everyone, my name is Rasul and today I'm going to be presenting our paper titled Practical Over Threshold Multi-Party Private Set Intersection. This is a joint work from me and my colleagues here at the University of Waterloo and are calling it Airbus in Germany. So private set intersection is a pretty well-studied problem, and in its simplest form, we have two parties, each owning some set, and the goal is to calculate the intersection of the two sets such that nothing beyond the intersection of the two sets is revealed to either one of the parties. So there's a variety of solutions for the different setups of this problem, for example, where we have multiple parties or we have unbalanced set sizes. But the over-threshold private intersection is a bit different. Where in that case, we have m parties, each owning a set of size at most n, and we have some threshold t, and we are looking for the elements such that are in at least t out of the m sets, such that nothing beyond this intersection is revealed to either one of the parties. There aren't many practical deployments available for this specific variant private set intersection, and this is where our work will lie. So for motivation, consider the following use case. We have multiple network operation centers which want to collaborate with each other to identify threats that are common so that they can investigate them. So how they do that is they collect these common indicators of they collect these indicators of compromise, and they want to compare them with each other to identify those threats that are common. Now the problem is that due to privacy, they can't just release and share those indicators because they might contain some sort of sensitive information such as IP addresses. But also the normal intersection might not be enough, because let's say half of the network centers have some indicator. It's not like they all have them, but it's still a threat that's worth looking into. Hence, the normal intersection may not be enough. So for related work, Kistner and Song proposed a method based on representing the sets with polynomials, and their method runs with communication rounds on the order of the number of parties and communication complexity, but with a pretty high communication complexity. There's another method using multi-party computation on the secret shared elements, which has less communication rounds but still has a pretty high communication complexity. Our work, which we call t-PSI or t-PSI, has constant communication rounds and has a communication complexity on the order of nmtk, where k is the number of key holders, or can also be called the collusion threshold, which I'll get into details of what this actually is in the next slides. So from here on, I'm going to be describing our work. First of all, our new primitive, Oblivious Pseudorandom secret sharing. Then I'll go over the Oblivious Pseudorandom private set intersection, the over-threshold private set intersection protocol that we've designed. First, t-PSI 0, and then following that, t-PSI, which is the more practical version, and their respective trade-offs. And then I'll go over the our experiments and evaluation, which show how our protocol scales. So first of all, to describe our primitive, the Oblivious Pseudorandom secret sharing, I first have to go over Oblivious Pseudorandom functions. Let's say we have some key holder which holds some private key k and a user which holds some private element x. The goal is, after some interaction, the user obtains some pseudorandom function of keyed by the key holder's key k of its own element x. And the goal is that all of this happens while the key holder learns nothing about the user's element x, and the user remains completely oblivious to the key holder's key k. Now, an Oblivious Pseudorandom secret sharing protocol is somewhat similar, but has a key difference. The user obtains not the pseudorandom function, but obtains a secret, a share of some public or maybe private secret. But the share generation process depends on that pseudorandom function keyed by the key holder's key k of the user's element x. Now, since I'm mentioning the use of some secret share generation procedure, corresponding to that is some reconstruction procedure for reconstructing the secret using the secret shares that have been generated. And this is going to be an integral part in our protocol as well. But to get a more concrete idea and to see an example, and to also see how this will relate to our protocol later on, take this example where we have 6 parties, and some of them have some elements in common. And we have a threshold of t equal 4, meaning that we're looking for elements that are common in at least 4 out of the 6 parties. Now, Now, how our protocol would work is we let each of the participants communicate with some keyholder and obtain a secret share of some secret based on the element that they owned. For this case, we'll use a T out of M threshold secret sharing scheme for the secret share generation. Now the thing is, if someone were to come and collect the shares generated by these participants and put them through a reconstruction procedure, if the shares were generated using the same element, then the reconstruction procedure would be successful, hence meaning that those shares corresponded to the same element. And hence that element would be in the T threshold set intersection. Also, on the other side, if not enough participants have a common element, then a reconstructor would not be able to reconstruct the secret using the elements that it has gathered from the participants. Hence, that element, not only is that element not in the T threshold set intersection, we would not be able to infer any extra information about the parties, the elements that the parties own. So back to our primitive. We discussed the case where we had one key holder, but it's also important to note that we can also have multiple key holders where instead of the key holder holding one key, the set of key holders jointly own some key, and the user interacts with the set of key holders altogether. So we constructed two variants of this primitive. The first variant, which has a simpler share generation process and runs in only one round of communication with communication complexity on the order of number of key holders, has a pretty costly reconstruction step, but this is what we'll be using in t-PSI 0. The second variant has a more complex share generation process with 2 rounds of communication and O of KT communication complexity, but has a much more efficient reconstruction procedure, which can be up to 1,000 times faster, and this is what we'll be using in t-PSI, which is much more practical. Okay, now onto the protocol itself, and I'll first go over the setup, where we have M participants, which are the owners of the data, and each of them own some set of size at most n. Then we have K key holders, which jointly own some key. And finally, we have the reconstructors, which can be seen as the ones that have more computation power. So an important note is that although we have these 3 separate entities, they can also overlap, meaning a participant can also be a key holder or a reconstructor, but we do have some assumptions on the collusion. For example, if we have one key holder, that key holder can't simultaneously be a reconstructor, or if we have more than one key holder, all K key holders can't simultaneously collude with the reconstructors. But for more details on the collusion assumptions that we have, I refer you to our paper. Also, for our protocol, all entities are assumed to be semi-honest. Now, onto the protocol itself, which has 3 very important steps. First, the share generation, which is conducted between each participant and the set of key holders. So, a participant, for each of the elements that they own, run the primitive that I described for that element to obtain a secret share based on that element. And they do that for all the elements that they own. So for t-PSI 0, we use the first variant of our primitive that I described, and in t-PSI we use the second one. Then we go on to the second step, which is the hashing to bins phase, which is done by each participant individually, and is a pretty common technique for private computation. So we have this predefined number of bins named B, and the user kind of distributes the elements that it has across these bins using some sort of like function such as a hash function, and each element is assigned to some bin number. Then for privacy reasons, these bins are padded to some maximum size that is again chosen by the protocol. And the reason for that, like I said, is privacy, because if one were able to see the load of the bins coming from one specific user, they might be able to infer some information about the elements that user owns. It's also important to note that the number of bins, which I said is chosen by the protocol, it represents a trade-off between the communication and computation as well, but I refer to details of that trade-off. I refer for details of that trade-off to our paper. Finally, we have the reconstruction step, which is done by the reconstructors on the shares that they receive from the participants. Specifically, a reconstructor for a given bin number and for some combination of participants takes all the different combination of shares that they can get from those participants in that specific bin, and run the reconstruction procedure over that combination of shares. Now, the thing is, based on the intuition I gave earlier, if the shares that the reconstructor has collected correspond to the same element, the reconstruction procedure will be successful, meaning that the element that corresponds to those shares is in the t-threshold set intersection, and in that case, the reconstructor reports back to the users, telling them that the element that corresponds to this share that I had that I got from you is in the answer. In t-PSI 0 and t-PSI, respectively, we run the reconstruction procedure using for the first and second variant of our primitive, where in t-PSI 0 it's a bit slower, and in t-PSI it is much faster. It's important to note that we are writing this protocol for all the different combinations of shares that we can get, which can be a bit a lot, but because we're using very cheap operations, it can be done very quickly, and it can be easily parallelized across as many reconstructors as we want, which can make it very scalable and practical. So finally, for our experiments, we calculated the runtime amongst other things to see how our method scales. On the left, you can see how our method scales to millions of elements in terms of the set size. Specifically, for the red, purple, and brown trend, you can see how it scales to millions of elements. And on the right, you can see how t-PSI scales to thousands of participants, specifically in the green trend. It's important to note that t-PSI outperforms t-PSI 0 in all of our experiments in terms of runtime. So to conclude, I explained a new primitive, the OPR-SS, for generating pseudorandom secret shares of a function. I described our two protocols, t-PSI 0 and t-PSI, and their respective trade-offs. And I described our experiments and evaluation and how they show that our protocol scales up to millions of elements and thousands of clients. Our code is publicly available on GitHub, and I invite you to take a look at it yourself and run some experiments. And with that, my presentation is over. Thank you for listening, and I'll be happy to take any questions you may have.